Your smart lights freeze mid-scene, your climate controls go dark, and your security sensors stop responding, all because the power blinked for 3 seconds. Power outages don't just kill your lights, they shatter the invisible choreography that makes a smart home feel effortless. I go by Keiko Tanaka, and I spend my days designing homes where technology disappears into the architecture, which means I've learned the hard way that backup power isn't optional, it's foundational. You're listening to Smart Home Setup Podcast. Quick heads up before we dive in. The research, the data, every word of the script, that's all human, verified by real experts who do this work. But the voice you're hearing right now, that's AI generated. Just wanted to be upfront about that from the start. If you've been listening for a while, thank you. It's genuinely great to have you back. And if this is your first episode, welcome aboard. New episodes drop every Monday, Wednesday, and Friday, so there's always something fresh coming down the pipeline. Today, we're talking about how to calculate battery runtime for your smart home so your automation doesn't collapse the second the grid hiccups. Let's get into it. Power failures interrupt the seamless rhythms of automation. Lighting scenes freeze mid-transition. Climate control halts. Security sensors fall silent. Understanding how to calculate UPS runtime for smart home infrastructure ensures continuity when grid power fails, preserving not just connectivity, but the invisible choreography of daily life. This guide walks through the precise methodology for determining battery backup duration across Zigbee coordinators, Wi-Fi access points, Z-Wave controllers, and thread border routers, translating wattage consumption into real-world protection intervals. You're looking at about 45 to 60 minutes to work through this properly. You'll need intermediate skills, basic electrical measurement and arithmetic. What you'll walk away with: accurate runtime predictions for every automation hub in your infrastructure, plus a framework for scaling backup capacity to your actual power failure patterns. First, let's talk about what you'll need to gather. On the measurement side, you'll want an AC power meter. Something like a kilowatt electricity usage monitor works perfectly for measuring real-time wattage draw. Check the link below to see the current price. You'll also need manufacturer spec sheets for each hub and router, usually available as PDFs on support sites, plus a calculator or spreadsheet application. For system documentation, grab your current UPS model specifications. You're looking for battery capacity listed in volt-ampere hours or watt-hours. Make a list of all devices connected to each UPS unit and sketch out your network topology showing which hubs depend on which infrastructure. If you've got historical power outage data from your utility provider, that's helpful too. Same with smart home power monitoring data if you've already got that deployed. Now, let's talk about measuring actual power consumption for each hub. Here's the thing. Manufacturer specifications rarely reflect real-world draw. A Zigbee coordinator listed at 5 watts might idle at 2.3 watts, then spike to 7 watts during network formation events. Connect each hub individually to a power meter for 24 hours to capture its consumption pattern across different operational states. Different protocols behave differently. Zigbee coordinators, think SmartThings, Habitat, Home Assistant with a Zigbee radio, typically draw 2 to 6 watts at idle. During device pairing or mesh healing, consumption may double momentarily. The SmartThings AOTech Smart Home Hub averages about 4.2 watts in steady state with 40-plus connected devices. Check the link below to see the current price. Z-Wave controllers like AOTech or HomeSeer range from 3 to 8 watts depending on whether they're using 500 series versus 700 series chipsets. Z-Wave Plus devices support beamforming, which increases momentary power draw during status updates. Long-range Z-Wave controllers consume 15 to 20% more than standard implementations.
Wi-Fi access points are the infrastructure backbone that every protocol ultimately depends on. A dual-band mesh node draws 8 to 15 watts. Tri-band models with Wi-Fi 6E consume 12 to 22 watts. These remain your highest continuous load. Thread border routers like HomePod Mini or Google Nest Hub are low power by design, typically 2 to 4 watts. Apple's HomePod Mini draws approximately 2.8 watts when actively routing Thread network traffic. Matter controllers depend entirely on the underlying protocol. Since Matter operates over Thread, Wi-Fi, or Ethernet backhauls, consumption mirrors whichever foundation you're using. Matter over Thread mirrors Thread consumption. Matter over Wi-Fi mirrors Wi-Fi patterns. Record the maximum observed wattage, not the average. Runtime calculations must accommodate peak demand to prevent premature shutdown during mesh network healing or firmware updates. Moving on to calculating total connected load in watts. Sum the maximum wattage of every device connected to each UPS. This includes not just smart home hubs, but supporting infrastructure, cable modems, Ethernet switches, NAS devices storing local security footage, and any subscription-free security cameras with local recording. Here's where critical dependency mapping comes in. If your Zigbee hub connects via Ethernet to a PoE switch, that switch must remain powered or the hub loses connectivity regardless of its own backup power. Many invisible automation failures trace back to overlooked infrastructure dependencies. I've consulted in homes where residents invested in hub-specific UPS units while leaving the primary router unprotected. Let me walk through a realistic example. Wi-Fi 6 mesh router at 14 watts, Wi-Fi satellite node at 11 watts, Zigbee coordinator like a Habitat C8 at 5 watts, Z-Wave controller like an AOTech Gen 7 at 6 watts, an 8-port managed Ethernet switch at 9 watts, and a cable modem at 12 watts. Total connected load, 57 watts. Add a 10% safety margin for measurement variance and aging component drift, so 57 watts times 1.10 equals 62.7 watts effective load. For homes with concealed smart home hubs hidden in millwork or cabinetry, verify adequate ventilation around UPS units. Battery efficiency degrades rapidly above 77 degrees Fahrenheit ambient temperature. Next step, identifying battery capacity in watt-hours. UPS specifications list capacity in one of 3 formats: volt-ampere-hours, ampere-hours, or watt-hours. To calculate runtime properly, all values must be converted to watt-hours. From volt-ampere-hours to watt-hours, you multiply VAH by power factor. Smart home hubs present near-unity power factor loads, minimal reactive power, so use 0.90 as the power factor for conservative estimation. A 450 VAH UPS becomes 450 times 0.90, which equals 405 watt-hours usable capacity.
From amp-hours to watt-hours, you multiply AH by battery voltage. Most consumer UPS units use 12-volt lead-acid batteries. A 9 amp-hour battery yields 9 times 12, which equals 108 watt-hour capacity. Battery chemistry introduces efficiency losses. Lead-acid batteries, the most affordable UPS models, assume 80% usable capacity due to voltage sag under load and deliberate depth of discharge limiting to extend battery lifespan. A 405 watt-hour rated battery delivers approximately 324 watt-hours before the UPS triggers low battery shutdown. Lithium iron phosphate batteries, premium models like the CyberPower OR500 LCDR M1U, deliver 95% usable capacity with flat discharge curves, allowing deeper, safe discharge. These cost 2 to 3 times more, but provide 30 to 40% longer runtime per watt-hour. For homes prioritizing aesthetic integration, consider whole home battery systems with dedicated smart home circuits. These eliminate visible UPS units entirely while providing hours to days of runtime depending on solar integration and battery capacity. Now we get to the core formula. Runtime in hours equals battery capacity in watt-hours times usable percentage divided by total load in watts. Using our earlier example, battery capacity 405 watt-hours from that 450 VA UPS, usable capacity 405 times 0.80 equals 324 watt-hours for lead-acid chemistry, total load 62.7 watts. Runtime 324 divided by 62.7 equals 5.17 hours, or 5 hours and 10 minutes. This represents steady-state runtime under continuous load. Real-world performance varies based on several protocol-specific factors. Let's talk about accounting for protocol-specific power surge events. Smart home protocols exhibit nonlinear power consumption during specific operations that standard UPS runtime calculators ignore. These events reduce effective battery runtime by 8 to 25% depending on mesh density and automation complexity. Zigbee mesh healing, when AC power fails and then briefly flickers, brownout conditions, Zigbee coordinators initiate network-wide route recalculation. For networks with 30-plus devices, this can spike coordinator power draw to 180 to 250% of idle consumption for 45 to 90 seconds. If your automations include smart lighting scenes triggered by power restoration, these compound the surge. Z-Wave network-wide inclusion mode is less common during outages, but if your automation logic includes if power restored, then heal network, which is recommended practice, expect 2 to 3 minute surges at 150% normal draw. Wi-Fi client reconnection storms are the most significant drain. When a mesh router on UPS power cycles, every Wi-Fi device, including Matter over Wi-Fi endpoints, cloud-dependent smart switches, and IP cameras, attempt simultaneous reconnection. A router serving 40-plus clients may draw 200 to 300% of rated power for 3 to 5 minutes during this stampede. Thread network reformation has lower impact due to the protocol's sleeping router architecture, but border routers still experience 30 to 60-second surges at 140% baseline when rebuilding partition tables. Mitigation strategy: reduce calculated runtime by 15% for mesh-heavy environments to accommodate these surge events. Our previous 5.17-hour calculation becomes 5.17 times 0.85, which equals 4.4 hours realistic runtime, or 4 hours and 24 minutes. Moving on to validating your calculations with real-world testing. No calculation substitutes for empirical verification. Schedule a controlled power failure test during low-stakes hours. Here's the test protocol. Disable all non-essential automations temporarily: irrigation controllers, robotic lawn equipment. Trip the breaker feeding your UPS units while monitoring start time. Observe hub status LEDs and network connectivity via a battery-powered device. Record timestamp when UPS begins alarm or warning tones, typically at 20% battery remaining. Record total runtime until UPS shutdown. Restore power and document any mesh network recovery behaviors. Expected variance: real-world runtime should fall within plus or minus 12% of calculated predictions for UPS units less than 2 years old. Larger discrepancies indicate battery degradation or measurement errors in your initial power consumption readings. Protocol recovery observations matter. Zigbee networks with proper mesh topology recover within 30 to 90 seconds of power restoration. Z-Wave networks take 45 to 120 seconds due to sequential node polling. Matter over thread mirrors thread timing at 45 to 75 seconds. Wi-Fi infrastructure typically restores fastest at 15 to 45 seconds, but dependent smart devices lag during the authentication and IP assignment phase. Thread and Matter devices exhibit superior graceful degradation. Even if the border router loses power, Thread, Sleeping, and devices maintain their mesh relationships and resume instantly when the border router returns. Zigbee and Z-Wave networks experience more significant disruption if the coordinator powers down. Now let's talk about designing tiered backup based on protocol priority. Not all hubs require equal runtime. Strategic tiering extends protection for critical systems while managing UPS investment costs. Tier 1, maximum runtime target 4 to 8 hours. Wi-Fi infrastructure, including modem and primary router. Security system hub and monitoring cameras. Zigbee or Z-Wave coordinator if it controls door locks, smoke detectors, or leak sensors. Tier 2, moderate runtime target 2 to 4 hours. Mesh satellite nodes supporting important zones like bedrooms and primary living areas. Climate control interfaces, thread border routers managing safety-critical endpoints. Tier 3, minimal runtime target 30 to 90 minutes. Ambient lighting controllers, entertainment systems, smart devices, irrigation and outdoor automation hubs. Implementation approach. Use separate UPS units for each tier, sized precisely to their load and target runtime. A Tier 1 hub cluster drawing 35 watts, requiring 6-hour runtime, needs 35 watts times 6 hours, which equals 210 watt-hours minimum, or 262 watt-hours, accounting for 80% battery efficiency. That's equivalent to a 290 VAH UPS. In-wall or furniture-integrated UPS systems eliminate visible battery boxes. Several manufacturers now offer shallow-depth backup modules designed for millwork integration. These mount behind credenzas, inside built-in desks, or within media console back panels. Pair these with hidden smart plugs for completely concealed backup power pathways. Next critical step is monitoring battery health and recalculating quarterly. Battery capacity degrades 15 to 25% annually in typical residential conditions. Schedule quarterly runtime verification to detect degradation before it impacts actual outages. Automated monitoring approach. Deploy a smart home energy monitoring system with UPS-specific monitoring capability. Configure alerts for runtime predictions falling below your minimum threshold. Track battery replacement intervals, typically 3 to 5 years for lead-acid, 8 to 12 years for lithium chemistries. You can build automation logic for battery health. If UPS runtime calculation falls below minimum acceptable hours, send notification to primary user and home dashboard. Log battery age and last replacement date. If battery age exceeds manufacturer service life, add replace UPS battery to maintenance queue and escalate notification priority to urgent. This logic integrates cleanly with Home Assistant, Habitat, or SmartThings platforms. For homes using Matter-native controllers, battery monitoring requires a compatible power meter since Matter 1.4 doesn't yet define native UPS device types. Temperature impact is significant. For every 15 degrees Fahrenheit above 77-degree ambient temperature, battery service life decreases by approximately 50%. If your hubs hide in enclosed cabinetry without ventilation, install passive convection vents or small thermostat-controlled exhaust fans to maintain sub-80-degree conditions. Let's cover some pro tips and common mistakes. The most overlooked calculation error, failing to include Ethernet switches in total load calculations. A managed 8-port switch may draw 9 to 12 watts continuously, more than many Zigbee coordinators. I've worked with clients whose meticulously calculated runtimes fell short by 40% because they powered hubs but forgot the network backbone connecting them. Power factor confusion. Don't use the UPS's output VA rating directly as watt capacity. A 900 VA UPS with 0.6 power factor delivers only 540 watts maximum. Attempting to draw more triggers immediate overload shutdown. Smart home loads present excellent power factor, 0.9 to 0.95, but verify your specific UPS specifications rather than assuming.
Battery age blindness. A 5-year-old UPS with never replaced batteries retains perhaps 40 to 60% of original capacity. Calculate runtime using actual current capacity, not the nameplate rating from purchase date. The Battery University maintains authoritative degradation curves for all common chemistries. Protocol-specific mistake for Zigbee.
Coordinators with USB power inputs often accept wide voltage ranges, 4.5 to 5.5 volts, but deliver peak performance only at 5.0 volts plus or minus 2%. Generic USB ports sometimes output 4.8 volts under load, causing subtle mesh instability. Use the coordinator's AC adapter plugged into standard UPS outlets instead. Protocol-specific mistake for Z-Wave. 700 series controllers draw higher instantaneous current during transmission than 500 series chipsets, occasionally triggering nuisance UPS alarms if the unit interprets this as a short circuit condition. Size UPS capacity at least 3 times the Z-Wave controller's peak draw to avoid false alarms. Hidden runtime killer. Smart home hubs often host add-on USB devices, Zigbee dongles, Z-Wave sticks, Thread radios. A Raspberry Pi running Home Assistant might measure 8 watts alone, but add 3 USB protocol radios and power draw climbs to 14 watts. Measure the complete assembled system, not just the base computer. Climate consideration. Runtime calculations assume 72 degrees Fahrenheit ambient temperature. Battery capacity drops 20 to 35% at 40 degrees, relevant for unheated utility rooms or detached workshops. If your Zigbee coordinator lives in the garage controlling autonomous yard equipment, account for temperature-adjusted capacity during winter months. Let me address some frequently asked questions. How do I calculate UPS runtime for a smart home with multiple protocol hubs on one battery backup? Measure each hub's power consumption individually using an AC power meter. Sum all connected device wattages, including routers and switches, add a 10% safety margin, then divide the UPS battery capacity in watt-hours by this total load. For a 450 VAH UPS with 80% usable capacity, that's 324 watt-hours, supporting 65 watts total load, 324 divided by 65 equals approximately 5 hours of runtime under steady state, or 4.25 hours, accounting for protocol mesh healing surge events that occur when power fails or restores. Does the smart home protocol choice, Zigbee versus Z-Wave versus Thread versus Wi-Fi, significantly affect backup power runtime? Protocol choice affects runtime indirectly through 2 mechanisms: baseline power consumption and surge behavior during network events. Wi-Fi infrastructure consumes 3 to 5 times more power than low-power mesh protocols like Zigbee or Thread, dramatically reducing runtime. A Wi-Fi mesh system might draw 25 watts while equivalent Zigbee coverage uses 6 watts. However, Wi-Fi routers typically recover faster after power restoration, 15 to 45 seconds versus 45 to 120 seconds for Z-Wave, reducing the cumulative impact of surge events across multiple short outages. Should I calculate separate UPS runtime for my Zigbee coordinator versus my Wi-Fi router, or back them up together? Separate UPS units offer superior runtime optimization, but introduce dependency risks. If the router loses power while the Zigbee hub remains powered, cloud-dependent automations fail and remote access breaks even though local mesh control continues. For most residential deployments, back up all network infrastructure together: router, switch, modem, and all protocol coordinators using a single appropriately sized UPS, then add secondary smaller UPS units for remote mesh satellite nodes or detached building hubs that serve independent automation zones like workshops or pool equipment. How often do I need to recalculate UPS runtime as my smart home devices age? Recalculate quarterly during the first year after UPS installation to establish a degradation baseline, then shift to semi-annual verification once you understand your specific battery aging pattern. UPS batteries degrade 15 to 25% annually under typical conditions, so a system delivering 5-hour runtime when new provides approximately 3.75 to 4.25 hours after 2 years. Plan battery replacement when runtime falls below your minimum acceptable threshold, typically when measured capacity reaches 60 to 70% of original specification, which occurs after 3 to 5 years for lead-acid batteries or 8 to 12 years for lithium iron phosphate chemistries. Here's what this all comes down to. Learning to calculate UPS runtime for smart home infrastructure transforms backup power from vague reassurance into precise, verifiable protection. By measuring actual consumption across Zigbee coordinators, Z-Wave controllers, Thread border routers, and Wi-Fi mesh nodes, then accounting for protocol-specific surge behaviors and battery efficiency, you create runtime predictions accurate within plus or minus 12% of real-world performance. The process requires initial measurement effort, but yields permanent benefits: right-sized UPS investments, tiered backup strategies that protect critical systems longer, and quarterly verification rhythms that catch battery degradation before actual outages expose the gap. Automation shouldn't announce its presence through failures when power flickers. Proper runtime calculation ensures the invisible intelligence woven through your spaces continues its work regardless of grid stability.
That wraps up this episode of Smart Home Setup Podcast. Thanks for spending this time with me. We've got new episodes coming at you every Monday, Wednesday, and Friday, so there's always more on the way. If this one helped you out, I'd really appreciate it if you could leave a 5-star rating and write a quick review. It actually makes a difference in helping other people find the show when they're searching for this kind of detailed, practical smart home guidance. And hey, hit subscribe or follow so you get notified the second a new episode drops. Thanks again, and I'll catch you on the next one.